Greetings to our fellow juries and audience. My name is Muhammad Luliwaudin bin Abdul Latif. I'm from the Department of Electronic Faculty of Electrical and Electronic Engineering, University Tun Sen On, Malaysia. So I'll be presenting continuous data collection of UnderExtrusion in FDM 3D printers for Deep Learning Dataset. A shortcoming noted in fused deposition modeling FDM 3D printing technology refers to lack of intelligent monitoring and intervention during the printing process. Failed prints can still occur during the printing procedure even though the printer is of industrial grade and far more expensive than hobby grades. The printer actually continue their printing jobs while ignoring any defect on the printed model. Thus, quality control has remained a significant challenge in additive manufacturing, which also known as 3D printing. Despite the apparent factors of FDM 3D printers, which can easily fabricate real parts within a shorter period at lower cost when compared to conventional manufacturing methods, they still fall short of any sort of intelligence required to detect and discern failures in the printed model during printing operations. Under-extrusion has been determined as one of the frequent failures in 3D printing. It may result in undesired layer gaps, missing layers, unbalanced layers, and even holes in the printed model. Such failure stems from insufficient extrusion rate and adequate melting temperature of filament during the print. An effective method that can reduce waste materials and overall cost by integrating artificial intelligence into the 3D printers. A large dataset is required prior to the training process of deep learning. Hence, this study proposed an automated and continuous data collection of under-extrusion samples in FDM 3D printers using Raspberry Pi and HD webcam. As a result, adjustment of the G-code of the standard tessellation language (STL) models and repeated process of printing 3D models can effectively achieve the desired image. Extrusion can yield missing layers, unbalanced layers, and layers with random dots and holes in the printed item. So there are many variables to consider such as G-code modification to result in under-extrusion printed samples such as temperature, manual disturbance towards the hot bed, flow percentage of the filament, the speed, a grinded filament, clock nozzle, and the filament diameter. So for the system architecture, extruder heating can initiate a certain amount of heat based on user preferences before the printing process begins. So octal labs capture image during printing runtime until the end of printing instruction. So in continuous printing, ejection instruction is initiated before the printing a new item, while the extruder returns to standby position and is set to home position. So for the G-code introduction, G-code is a language that one uses to instruct machines on how to perform tasks. So G-code is applied in 3D printing to move pieces within the printer. G-code is made up of G and M commands to each has a specific movement or action. Both G and M codes are included commands in the file to instruct the printers on how and where to extrude the material. The sole distinction is that the G codes are generally understood by printers that use G code, whereas M codes are particular to each printer line. So for the E-steps modification, E-steps should only be modified to assure dimensional precision, while flow rates should be adjusted to accommodate for material and model requirements. Physical movements such as distance moved and filament extruded through the extruder were applied to calibrate E-steps. The volume of filament going through the extruder was affected by E-steps adjustment. In this paper, the volume of filament going through had reduced by 40% from its initial value to purposely cause under-extrusion. The parameter for new E-step was calculated as follows. So for the G-code modification, with the latest value of E-steps, G-code was altered to a condition where the printed samples indicated under-extrusion type of failure. So a user has to state the extrusion command and the initial value of E-steps under the home command, which will move the axis to their true zero position or home. This line can be used repeatedly to bring the initial volume of filament that passes through the extruder at certain layers. So for the layer alteration, relapse to previous section, the initial value of E-step was introduced at the start of G-code under the homing command. So new E-step value generated an under-extrusion condition beginning from the certain layers that have been set until a new command of initial E-steps was initiated. So this is the layer alteration. As you can see, these generated layers at under-extrusion and normal condition. From this set of G-code modification, the printed samples were as follows. Layer 1 to layer 39 were the normal layers. Layer 40 to layer 59 were under-extrusion layers. And the layer 60 until the end were normal layers. So for the Octoprint for remote control system, Octoprint is a popular technique to transmit G-code commands to 3D printers and to observe print status through the live feed. And it uses a serial RS232 connection to communicate with the printers and can upload already sliced models for printing using online interface. So for the results, AutoPrint generated a real-time view of printing algorithm and instruction by using the web interface. As you can see here, the first image, the nozzle head was set to center and lowered to the back of the model before start pushing in a positive manner for the model ejection. But in order to avoid the error in ejection, the print bed was cooled down to 30 degrees Celsius. The variance between under-extrusion layer and normal layer is vivid in this image as the flow rate of the filament decreased to 40%. This is crucial in the system to effectively and accurately identify the fault. So with a large margin of differences between the rates of filament, both normal and under-extrusion layers were very fragile towards each other. So the detachment between the layers seems possible if not handled with care. So in comparison to previous research in citation, this method proved to be easier. So for the conclusion, in this paper, an automated system 3D printer algorithm for under-extrusion fault detection is proposed. So upon incorporating G-code modification, continuous monitoring printing, monitoring plugin system, a foundation system is proposed for the automated printing fault detection system. Both challenges and factors that could possibly affect the performance of the system while experimental work is called for to generate a fault detection system. Overall, advances in FDM 3D printer fault detection system have proven many positive outcomes. Despite that, the further investigation is in need to enhance the technology for broad application in engineering 3D printer. For the acknowledgement, this research was supported by Ministry of Higher Education, Malaysia through the Fundamental Research Grant Researcher. That's all from me. Thank you.